Hey guys, welcome to video 4.2. In this video, we are going to talk about how we can apply everything that we've learned about vectors and apply it to things that we already know about forces. So I'm going to start with a basic force problem, and I'm going to walk you guys through the steps on how to solve this problem. Now, the steps aren't always exactly the same for every single problem, but the basic steps are kind of similar. So the first step you need to do anytime you're dealing with any kind of force problem is draw the free body diagram. So in this example, it says a box is being pulled upward and to the right with a force of 80 newtons at an angle of 30 degrees. All the forces are given to you in this problem. So let's say here is a box, but it's being pulled at an angle of 30 degrees. So here's my box. Okay, it's being pulled, so there is a tension force, and normally if it's being pulled just to the right, we would show an arrow this way. If it was pulled up, we'd show an arrow this way. But it's being pulled upward and to the right. So we're going to show a diagonal arrow for our tension force. And it says that we're pulling with a force of 80 newtons. Okay. The angle is 30 degrees. So I want you to include the angle on your free body diagram. All forces are given to you in this problem. So I forgot to write them down, but to type it out for you. But here are also the forces that are given. Okay. So let's pretend I typed it out. The force of gravity is 98 newtons. The normal force is actually not the same as the gravitational force in this example. The normal force is 58. The friction force is 40. Okay, so now that we have all these, let's label them all. So normal force, that's kind of, goes straight up, and it's 58. Gravity goes straight down, and it's 98. And then friction goes this way because it's being pulled this direction. So friction's going the opposite with 40 newtons. It doesn't say what it wants you to solve for here, but it wants you to solve for your net force. What's your net force? Well, normally net force, you can have two ways to calculate it. It could be mass times acceleration, but we're not given mass or acceleration, so we can't use this formula. So the other formula was adding all our individual forces together. Well, the problem with doing that is we can only do that if there's an unbalanced force in only one direction. For example, if there's an unbalanced force up and down, which we can see that it is, then we can find net force by adding them all together. But as you can see, that's not the case. We have an angled force, which means we can't add them all together. We also have an unbalanced up and down and an unbalanced left and right. So all of that means we can't do the net force of adding our individual forces together. So since we can't do either of these formulas, we have to follow these steps. Okay, the first step is to draw the free body diagram, which we did. Second step, we want to change all force vectors that are angled into component vectors. So the only one that is angled right now is our tension force. Our normal force, our friction force, and our gravity force are not angled, right? They're straight up and down and straight left and right, which is great. We need this arrow right here. We need to have the component forces. We need to have the X and the Y forces. So it's being pushed up and to the right, so that means this guy's component vector goes this way and this way. So I'm going to pull any angled forces aside, and I'm going to find out what their up and their rightward force is. So let's redraw it. This is our angled force. Your angled force is always going to be H, okay? It's your resultant. And we know that the other two forces are going this way and this way because it's going up and to the right. So here's our x-axis, okay, right here. Where do we want to move our arrows so that it makes a triangle? Well, we're going to move this up and down arrow right here because we want to have a triangle where the angle is closest to 0 degrees right over here. That's 0, this is 90 degrees, 180, and 270. So we want the angle that's closest to 0. So here's our triangle. Now I'm going to redraw it. Here's our angle. We were actually given the angle, if you remember. It's 30 degrees right here. It said that it's being pulled at an angle of 30 degrees. So here's our angle, 30 degrees. We don't know our h. Actually, I lied to you. We do know our h. It tells us right here the force of this arrow is 80 newtons. So that is our h. Because it's referring to this line right here, right? That line was 80 newtons. So we have h. This is the opposite of the angle. This is the adjacent of the angle. That's what we need, right? We need these arrows here. So I remember they're arrows, so I'm going to go ahead and draw the arrows here like that. Okay, so how do I find my component vectors? Well, I'm given the angle and I'm given h, so we know we have these formulas. This formula here, I have my h, I have my angle, I can find O, and then I could also use this one. I have my h, I have my angle, so I can find adjacent. So let's rearrange. H times the sine of my angle will give me opposite, and then h times the cosine of my angle will give me adjacent. So let's go ahead and do that. H is 80 times sine, and my angle is 30. And so I get, for opposite, I get 40 newtons. And here's my opposite, and see how it's going upward? So it's 40 newtons up. And what's my adjacent? Well, it's going to be 80 cosine 30. That's my angle. And I get 69.28. So I'm going to do 69.3. What direction is that? Well, my adjacent looks like it's going to the right, so it's this to the right. So that is your second step. Okay, change all your angled force vectors into component vectors by using the Pythagorean theorem and trigonometry. Actually, in this example, we just used trigonometry. So next, we need to add all our component vectors, so we just have one up and down vector and one left and right vector. So I'm going to redraw my free body diagram. Okay, we have normal force going up with 58, looks like. We have gravity going down with 98. We have friction going left with, I forget what it is, 40. And then we have these two. We have to add these two. Okay, we're going to add these to the list. We don't have our angled force anymore because we've broken it into our two component vectors. So 40 newtons up. So the force of my tension part 1 is 40 newtons up. So this is my force of my tension. I'm just labeling it part 1 because both of these together make the force of my tension. So, you know, it doesn't matter which one's 1 or 2. My force that's going this direction is, that looks like it's angled, but it's not supposed to be, is 69.3, going to the right. So now I have all of these forces, and they're all not angled, right? They're all components, meaning they're all going up and down or left and right. But I want to resolve it so I only have one up and down and one left and right. So take the forces that are going up and down, and we're going to add them together. So the forces going up are 58 plus 40. The force going down is 98. Remember, that's negative 98. So I take 58 plus 40, which gives me 98. Minus 98 is 0. Okay. That is unfortunate because I actually wanted to get a number there. So I'm actually going to change my numbers a little bit. Let's change, because we actually need a number in order for this problem to work. So I'm going to change this to 100, okay? So sorry about that. I'm just switching out some numbers real fast. Let's change the gravity force to 100, just to make it fun. So now we end up with a net force of 2 newtons downward. Okay, 2 newtons downward. And, okay, so that was my up and down forces. Now let's do my left and my right forces. Well, my right force is 69.3. My left force should be a negative because it's going against my direction of motion. So this becomes 29.3 newtons. So now redraw your free body diagram again, okay? I have 2 newtons going down, and I have 29.3 newtons going this direction. Okay, that's important. Once we have 2 vectors, we have an up and down vector that we added together and a left and right vector that we added together. Now solve for the resultant vector. So whenever I ask for f of net is basically the same thing as the resultant vector from all the vectors. So we had all these vectors right here. We add them together, we end up with this resultant vector and this resultant vector. Now I want to add those two together. Well, they're going in different directions, so I can't actually legitimately add them, but I can use the Pythagorean theorem to figure out my resultant vector, and I can use trigonometry to find the angle. So what do I want to do? Which of these arrows do I want to move? Well, I want to move this top one down, because, so it's going to look like this. I want to move the top one down because I'm looking at the angle that's closest to this. So this is 0 degrees. Remember, if this is 90 degrees, 180, 270. So I'm actually looking at the angle that's right here. I want this whole angle right here. So, but this box, if you can see, is only going to give me like a small angle. So I actually need to add this angle to the rest of this. Well, this is 90 degrees. This is another 90 degrees, so it's 180. And then this is another 90 degrees, so it's 270. So whatever this angle is, I want to add it to 270 to get my whole angle for my resultant vector. Okay. So this is opposite, this is adjacent, this is hypotenuse. We know these guys, right? What's A? A going downward is 2 newtons. Opposite is 29.3 newtons. How do I find H? Well, remember our formula, a squared plus b squared equals c squared. Probably a better way to write that formula is a squared plus o squared equals h squared. A and O stand for our component vectors, and H stands for our resultant. So let's go and do that. So 2 squared is obviously 4. What is 29.3 squared? Phew, it's a nice long ugly number. 58.49 equals H squared. So I add that to 4. And then I want to, square root both sides here. So it's H equals 862.49. 862.49. Square root it, and I get 29.4. That's my resultant vector. That's this guy, the red guy, is 29.4. That is my net force. So if I said, what's the net force? 29.4 is the net force. Now, if you want to find the angle of that net force, we now can use any of our formulas. I'll just use sine to find my angle. The reason I can use any of them is because I have A, O, and H. So since I have all 3 of these, it doesn't matter which trigonometry formula I use. If I want to find the angle, I can move sine to the other side right here. When I move it to the other side, it becomes the inverse sine. So it's sine inverse. So I plug that into my calculator, press second sine, and then what's my opposite? Was 29.3, and my hypotenuse was 29.4, almost identical. And so my angle is 85.3 degrees. Now that's not my final angle, is it? I need to go back here. 85.3 is actually only the angle right here. Okay? It's only this angle. So I need to add it to 270 to get my full angle. So I take 270 plus my angle, and I end up with 355 is the angle of my resultant vector. 355 degrees is the angle of my resultant vector. I kind of drew this incorrectly because I didn't know the angle at the time, so I just kind of drew it weird. But really, this red resultant actually kind of comes like this, right? Because it's almost 360 degrees. Okay, we're going to do another problem with forces in 2 dimensions. So in this problem, it says a train is going down a hill at an angle of 30 degrees. The object's mass is 1,000 kilograms. So the first thing we need to do is draw the free body diagram. So the train's going down a hill. So here's the hill right here. The angle of the hill is 30 degrees. Okay, here's my train. Always draw it as like a box sitting on your plane. Okay. So what forces are at play? Well, the box is sitting on the plane. So if here's the plane, we know that gravity, oh no, what just happened? Okay, so as I was saying, we know that gravity works straight downward. So here's gravity. It's going all the way down like this. Friction goes this direction, except I forgot to mention that this is a frictionless surface. So for this example, we're not going to use friction. So there's no friction. It's not being pushed. So the only thing that's happening is it's falling down. And on the surface, it's sitting on something, so there's also a normal force. However, the normal force does not go up like this. It doesn't go straight up. The normal force, when you're inclined, the normal force always goes straight up from wherever it's sitting. So it's sitting flat like this. So the normal force goes up this direction. It goes up straight from wherever it's sitting. So this is an example of a free body diagram where there's an angled force, because you can see that the force of gravity is going straight down, but the normal force is angled this way because we're on an angle. Okay, so we draw the free body diagram. Here's my normal force, like this. It's on a frictionless surface. The mass of the object is 1,000 kilograms. Okay, I don't know my net force, and I don't know my acceleration. I forgot to write this in the problem, but the problem is asking for what is the net force and acceleration. So we're looking for net force and acceleration. So when you have a problem like this, we need to change all the angled force vectors into the component vectors so we can add them up. But if it's on an inclined plane, you're still going to do this, but you actually need to turn the free body diagram to where gravity is the only angled force and all the other forces are straight up and down. So here, I'm going to take this. I wonder if I can do it. I'm taking this object, okay, and I want to turn it. I wonder if it'll let me turn it. Let's see. Nope, it's not going to let me turn it, but that's okay. I will just redraw it. Oh, there it is. Okay. I didn't want to lose my original drawing. Okay, so what I'm doing now is I'm going to turn this to where it looks like it's flat. Okay, so I'm turning it to where it looks like it's flat. The normal force goes up, and now it's the gravity force that's angled. Okay, so do you see how I just took this and I just turned it? It got turned! Actually, I don't know if that's a bad word, so maybe I should say that. Whoops. Okay, so this angle is 30 degrees, right? So whatever angle the incline is, so if you can turn it this way, you can see it sliding down. Whatever angle the incline is, that's going to be the angle of your force of gravity, by the way. Okay, so it's the same exact angle as the angle of your incline. So the force of gravity's angle is 30 degrees. So in order to determine my net force, I have to change my angled vector here and put it into component vectors. So I'm going to draw it off by itself. I'm going to do it like its own problem. Here's a force of gravity. Okay. And here's my x-axis. And let's say what are the component vectors doing? Well, one's going down and one's going to the right, right? Because this arrow is going down and to the right. So my component vectors, one's going down and one's going to the right. So now I need to rearrange them to show a triangle. So I want to actually move this angle right here. I want to move this arrow downward like this because I want the angle that's closest to this part of my x-axis. This is 0 degrees. This is 180. This is 270. So I'm actually going to have to add 270 to whatever this angle is right here. Okay. So I have my angle. Actually, I don't have my angle. I don't know why I said that. We don't, no we do. We do have the angle. Wow, I'm losing my mind here. The angle is 30, right? Our angle is 30 right here. This is 30. And then we're trying to find our component forces. Well, how do I do this when I'm not given any forces? Well, the force of gravity can always be found. So let's use our formula. Force of gravity is mass times g. They said in the problem that the mass was 1,000 kilograms right here. So my force of gravity is 1,000 times g. G is negative 9.8. So if I multiply it by 1,000, my force of gravity is actually 980 newtons. Negative meaning it's going downward. So F of g here was 980 newtons. That's also my hypotenuse, right? That's h. This is my O, and this is my A. So how do I find O and A? I'm going to use my formulas. The sine of the angle will equal opposite over hypotenuse. I have my angle, I have my hypotenuse, so I can find opposite. So I'll just rearrange to do h times sine of my angle gives me O. So h is 980 times sine of my angle, which is 30. And I get 968. So O is 968 newtons, and it's to the right. Okay, that's my O. How do I figure out A? Well, I'm going to do cosine of my angle is A over H. I have H, I have the angle, so I'll just rearrange. H times the cosine of my angle is A. So I do 980, that's H, times cosine of my angle, which is 30. And I get 151. So it's 151 newtons downward, right, down. So here's my two components. So now watch what I can do. So here's my free body diagram. I know that I go 968 newtons to the right and 151 newtons downward. So I don't actually need this gravitational force because I found my components, so I'm deleting this. Remember, our goal is we want to have forces that are up and down and left and right. That's what we want, up and down and left and right. Question though, we have downward force, we have the rightward force, those are the components of gravity. How do we know normal force? Well, normal force in this case is not the same thing as gravitational force. Notice in our first free body diagram, normal force and gravitational force are not going exactly opposite of each other, so they're not the same value. In this situation, normal force will be the same as the force going this direction. They'll be the same value. So when we flipped it and we found the components of our gravitational vector, these are the components that make up gravity, this component of gravity actually equals the normal force. So our previous formula of gravity equals normal force does not work on inclined planes. The normal force will equal whatever force is opposite it. So this 151 is the same as this normal force. So now I have to do step 3. add all my component vectors into one up and down vector and one left and right vector. So my up and down vectors. Well, up is 151 newtons, down is 151 newtons, so my net force up and down is 0. Okay, my left and my right vector. Well, my right vector is 968 newtons. My left vector is nothing, so my net force is 968 newtons. Okay, if we only, so then I redraw it one more time. Here's my free body diagram on the incline, right? And it has a no up and down force, but it has a left and right force this way. If you end up with only one vector, you're done. This is your resultant vector, which means it's also your net force. Okay? Yay! I didn't mean to cross it off. That was unfortunate. I meant to circle it, but I did such a terrible job circling. So if you get one arrow, you're great. Normally, though, you'll end up with an up and down arrow and a left and right arrow. If you end up with an up and down and a left and right, you solve just like we did this previous problem. Okay, we had an up and down vector that was 2 and a left and right vector that was 29, and we found our net force was our resultant. So since we already have our net force, that's awesome. We can now find our acceleration. So net force is mass times acceleration. Our net force was 968. Our mass is 1,000. What's our acceleration? Well, I take 968 and I divide it by 1,000. I don't know why I'm putting it in the calculator because I know the answer. So my acceleration is 0.968 meters per second squared. So you can still find the same types of things that we were finding last unit. It just takes us a little longer to find net force because we have to follow these steps to get our net force. Okay, I'm going to do one more problem with y'all, and that's it. Then, that's weird. Why is this not showing? Okay, then we'll be done. Okay, in this picture, I've already written the free body diagram for you, and, whoops, that's not supposed to be there. And I've changed it. So the first thing we do is we draw the free body diagram. It says a box is sliding downward. Okay, so here's my inclined plane right here.
The box is sliding downward on a plane with a friction force of 20 newtons.
So it gives us this. This is given. A normal force of 43 newtons. This is also given. And a gravitational force of 50 newtons. Also given. So in this case, I've given you all these, which is really great. And it says, what's the net force? It wants to know the net force. And it wants to know the acceleration. Well, first thing we do is draw the free body diagram. If it's on an inclined plane, you need to turn it. Okay, so when we turn it, notice that now we have only one force that's angled. Before, we had two forces that were at an angle. Okay, that would mean we'd have to take both of these and find their component vectors. That takes a lot longer. That's why we always want to turn it. When we turn it, gravity is the only angled vector that we have to find the components of. Okay, so it's really great. It's the only angled vector. Remember, once you turn it on its side and the gravity is the angled vector, when you find the two component vectors, the up and down ones, the one that's opposite of the normal force will be the same value. So before I even begin, I know my gravity is 50, and I also, guess what? I know what this guy is. I know this guy's force is 43. Why? Because it's got to be the opposite of the normal force. So now I'm going to redraw my triangle. Okay, this is 50. It's my H. This is 43. It's my adjacent. All I need to know now is my opposite angle. So I actually don't need to use trigonometry for this. I can do my formula. My hypothesis squared equals both my sides squared and added together. We just kind of ignore the negative. So 43 squared is 1849. And then 50 squared is 2,500. So I subtract it. So I get 641 equals O squared. So then I put them both in the radical. So the radical of 651 is 25. So O is 25.5 newtons. Okay, 25.5 newtons. So now that I have my vectors, I need to redraw my free body diagram one more time. Okay, and I draw it with my normal force, my friction force, and instead of drawing gravity like this, I'm just going to draw the components of gravity. There's a component this way, and there's a component this way, right? The component to the left, right here, is 25.5. The component upward was 43. Oh, it wasn't upward, it was downward, I'm sorry. Downward, because my resultant was this way. Downward, oh, how did I miss that at? Okay, to the left was 25.5. Downward was 43. And now I'm just going to copy. My friction was 20. My normal force is the opposite. So then I need to find my net force. In this case, it's pretty easy to find my net force because my up and down forces equal out to 0. And my left and right forces will give me 5.5 to the left. So I don't have to find the resultant vector in this example. So my net force is this. And now I can find my acceleration. The mass, what did they tell us the mass was? It didn't give us the mass, but if we wanted to find acceleration, we would have to have the mass. So you do mass, and then you could find your acceleration. That's it for our video. It's important that you know how to do all of these steps. Okay, you need to know how to draw free body diagrams. You need to know how to take the angled force vectors and break them into component vectors. You need to know how to add up all the component vectors. Hopefully you just get one vector when you add them all up. And if you do, then that's the net force. If you don't, if you get one up and down and one left and right, then you have to do one more step. If you have an up and down and a left and right, then you have to do one more step to find the resultant force. And you'd have to find the angle. If you end up with only one vector, like one up and down, or one left and right, well, you don't need the angle, right? Because you can just say up or right, okay? And you don't need a resultant vector because this is the resultant vector if you end up with only one vector. And that's it for our video. You do have one practice problem to do, and I'll go over it in class on Thursday. That's it. Have a good day.